reduce down a circle, I would say, well, you just truncate the zero modes on a circle. That's a consistent truncation. The zero mode sector of your Kaluza-Klein theory is consistent. I would say let's try to do the same thing over here. I have a whole Kaluza-Klein tower. If I truncate just the zero modes, I should get this. Unfortunately, it's not quite that simple. One thing you can realize is when I say these are zero modes, or when I say these are supergravity modes, if I look at the SO8 representation, this tells you what kind of spherical harmonic I have on the seventh sphere. 0, 0, 0, 0. This is a singlet. This is number 1 here. That's a singlet. These guys over here are not singlets. These are not singlets in SO8. So I cannot have a simple rule. Zero mode equals singlets of SO8. It doesn't work. Zero modes equals constant on SO8. Doesn't quite work either, because these are sort of a little bit non-trivial on SO8. This is the lowest Kaluza-Klein level, but they're still non-trivial on SO8. So a simple-minded rule, just truncate the singlets of my isometry group. It doesn't work. It doesn't give you supergravity. In fact, it only gives you the graviton over here. You can also say, well, if I had some massless levels over here, massless states over here, and a big Kaluza-Klein tower, I take the circle, I shrink it to zero size. All those tower states go up to infinite mass. They can decouple for the theory. I'm left with my zero modes. Well, here I can try the same thing. Take the seventh sphere, shrink the seventh sphere to zero size, decouple all the massive states. I'm left with the massless sector. There's a bit of a problem with that, which is this relation over here. The ADS radius and the seventh sphere radius are tied together. There's a numerical factor of 1/2, which is interesting, but doesn't change the argument. If I'm going to shrink the seventh sphere to zero size to get rid of the Kaluza-Klein modes, then I've shrunk my ADS space-time basically to zero size as well, or at least to very small radius, which is not a very physical thing to do in terms of having a large sort of not strongly curved four-dimensional space. Incidentally, this is also one of these features that sort of goes against this theory as originally constructed as being a bit of a realistic theory of compactification. Because this ties compact space to space-time through here. Normally you want large, weakly curved space-time and small, whether strong or not, but small internal space. This is sort of saying you can't quite do that using the Freund-Rubin construction. So I gave you at least two plausible arguments of why it's not so obvious and not so easy to come up with a consistent truncation to zero modes. Going to singlets doesn't work. Shrinking the seventh sphere down to zero radius doesn't quite work either. So there's no obvious symmetry principle to why I can compactify, truncate to n equals 8 supergravity and throw away the rest of the tower. Nevertheless, when we get this far, it feels natural enough that there ought to be a way to think if n equals 8 supergravity is consistent by itself, regardless of Kaluza-Klein, regardless of where it came from. If someone wrote down an n equals 8 supergravity Lagrangian, they said, at least at some classical level, this is a consistent Lagrangian to write down. And if 11-dimensional supergravity on a seventh sphere can give you this at the lowest level, then shouldn't it be possible to call this a consistent truncation? And the answer appears to be yes. And DeWitt and Nicolai more or less has proven that the full nonlinear reduction of S7 gives you this as a consistent truncation. There's one or two possible loopholes, but more or less, I think it's pretty much guaranteed that this is a consistent truncation. However, it's not completely obvious what the symmetry principle is, guaranteeing consistency. The opposite case, AS7 times S4 was proven to be consistent by explicit construction by these guys. I tried to at least hint a little bit that there's still things we don't really know about such a basic thing as the Freund-Rubin Freund-Rubin compactification. It's just, you know, this consistency question, things like that. It's not quite so obvious once we work with internal spaces that are curved or with fluxes like that. Let me go back to this idea of truncated singlets. By going to sort of a charge zero sector or a singlet sector of my internal space, I'm guaranteed to be left with a consistent truncation. If it's not going to have all these other fields, it cannot be supergravity. In fact, it cannot have any gravitinos at all, because the spinner 8s is not a singlet. So if I go to the singlet sector over here, I wipe out supersymmetry. Nevertheless, as a bosonic compactification, it ought to be consistent. If I go back to the Kaluza-Klein table, I find out there's another singlet, which shows up at the Kaluza-Klein level 2 over here, and it's a scalar field. The scalar field has an obvious interpretation. Well, it may not be obvious until you look at it, but once you look at it, it has an obvious interpretation. I wrote down the Freund-Rubin ansatz as a direct product. Here's ADS space. Here's S7. ADS times S7 or something. However, I can allow the volume of S7 to be changing as a function of a space-time field. So that's not exactly a direct product anymore. It's more like a warped product. And the volume of the ADS of S7, as it's changing in space-time, can be parameterized by a scalar field. And that's often called the breathing mode, in the sense of the sphere breathing or getting bigger or smaller. And so this turns out to be the so-called breathing mode scalar. And that gives you a nice hint. If I wanted to write down a consistent truncation, you know, a full nonlinear ansatz, I would do it like that. I'll write down a metric and a four-form potential. So the metric, if I forget about phi for the moment, is again an ADS metric over here and S7 metric over here. I even stuck in the radius factor for S7. And the idea of the breathing mode is to say the volume of S7 can actually vary. And since I want the metric to be sort of non-negative, instead of writing this as phi, I can write it as exponential phi, e to the phi. And then I can put in some constant factor. Beta is a constant over here, just for convenience. And you remember, yesterday I showed you in the circle reduction, I had to Weil scale the metric to get some nice sort of string frame or Einstein frame results. So I'm going to put in a possible Weil factor over here, e to the 2 alpha phi, in front of the space-time metric as well. So this is basically turning on a breathing mode, and this is just for convenience of providing a Weil scaling if needed. And a four-form field is proportional to a volume form. So this is the curved space epsilon tensor over here. That's the four-dimensional volume form. And compatible with symmetries, I'm going to allow myself to put in a breathing mode factor here as well. So I've inserted one breathing mode scalar phi, but I've done so with three constants, alpha, beta, and gamma. This is basically the only ansatz I can make compatible with the symmetry of S7. Going to the singlets on S7 is keeping this to be around S7. I'm not going to destroy or distort S7. The only thing I can do is multiply it by a scalar. So to see whether this reduction ansatz works or not, all we do is we plug it in to the equations of motion. And since the Einstein equation is always the most obnoxious one, we'll start with the form equation of motion. Again, it's proportional to the volume form. E to the breathing mode, e to the phi times the volume form, doesn't change the fact that the volume form is the top form in 4 dimensions. So it's closed, it's automatic. The equation of motion, d star f, is a little bit trickier. F wedge f is still equal to 0. So you're going to have d star f equals 0. The Hodge dual with the various dilettante factors in the metric gives you an equation kind of like that. This is a scalar set. So d of the scalar equals 0 more or less says the scalar is equal to the constant. So this thing inside here should be a constant. I want this to be a constant for arbitrary phi of x, for arbitrary breathing mode. And the only way to do that is to set my alpha, beta, gamma constants to be equal to 0. So I'm going to choose gamma so that this factor over here is equal to 0. This also tells you, and to go back to my ansatz over here, if I picked some random alphas and betas and I did not turn on this gamma factor over here, then it wouldn't really work. So I really did need to put in a gamma factor over here. Well, after looking at the form field equation of motion, you still have to look at the Einstein equation. So the Einstein equation, I copied it down again over here, is the 11-dimensional Einstein tensor being sourced by the 4 form over here. Now the 4 form being proportional to the volume form basically is exactly the same things I would have gotten before. This is a stress, this is just a reduction of the stress energy tensor using the Freund-Rubin ansatz. Except because I have these sort of work factors in front, I get these exponential phi factors that show up here as well. So I want to solve these two Einstein equations, basically. This is the 11-dimensional Ricci tensor. So what I need to do next is to calculate the 11-dimensional Ricci tensor for the Freund-Rubin ansatz, or for the breathing mode ansatz. This is a good exercise, but kind of a painful one. What you find is the 11-dimensional Ricci tensor has non-trivial components in space-time and on the sphere over here. There's no mixed components over here. And it's given by expressions kind of like that. The right-hand side are computed out of my 4-dimensional quantities. So this is the curvature of the 4-dimensional G mu metric. This is just the G mu metric. The Laplacian over here is a covariant Laplacian computed out of the 4-dimensional G mu metric, and so on. And remember, the metric had alpha and beta factors in it, alpha in front of space-time, beta in front of the sphere. So sure enough, alpha and beta factors show up when you actually compute the curvature. And it's a little bit ugly, but if you look at this, you find something a little bit interesting can happen. There's several lines which has this 2 alpha plus 7 betas. So if I make a choice to set 2 alpha plus 7 beta equals to 0, then I can get rid of long terms over here. Because e to the 2 alpha phi in front of G mu nu is a Weyl scaling of G mu nu, I'm basically allowed to choose alpha as I please. So I'm allowed by convenience to choose this condition to be true. It turns out that this choice corresponds to what's called the Einstein frame reduction, in which case my 4-dimensional Einstein-Hilbert action is canonical. It doesn't have a Brand-Sticky, or it doesn't have a scalar factor in front of it. So make that choice. Once I've fixed alpha and beta, then gamma gets fixed as well. So let's say I can rewrite everything in terms of alpha. So I go back to the Einstein equations. I've turned it around a little bit. The stress energy tensor I wrote over here on the left-hand side, and then the reduction of the Einstein tensor, or the reduction of the Ricci tensor I wrote down over here. So one thing is there's lots of possibly confusing notation over here. This is the 11-dimensional Ricci tensor computed from 11-dimensional metric. These guys over here, this is the 4-dimensional Ricci tensor in AES4, or whatever background I choose. This is the 7-dimensional Ricci tensor on the 7th sphere. The 7th sphere is round. And I've written my metric such that I wanted a unit radius of the 7th sphere. Maybe I shouldn't say unit radius, this is 2L radius over here. So the Ricci tensor on the 7th sphere is just given by the Einstein condition over here. I plug that in and end up with the space-time component of the 11-dimensional Einstein equation and then the 7-sphere component of the 11-dimensional Einstein equation. Like that. Because I have not destroyed the symmetry of the 7th sphere, the internal components of the Einstein equation all give you the same over here. There's an overall Gij that's factored out in this equation. Now these equations should not look completely crazy. If I start over here, this is box phi. This is a Klein-Gordon equation with a source, or rather, it's a Klein-Gordon equation with a potential over here. This is a scalar potential. And then that's the box phi part over here. So this is the scalar equation. This is a breathing mode scalar equation. And then this is the Einstein equation, the 4-dimensional Einstein equation, which has, obviously there's funny numbers here, so these are not canonically normalized. But this is a stress energy tensor for a scalar field over here. This is actually a Ricci form, but essentially it's a scalar equation over here. And then this is the potential energy term. So all these numbers conspire to work out perfectly. So this is a potential V of phi over here. This is the gradient of V of phi, which is the force term that shows up in the scalar equation. I can group that together and say these equations of motions can be obtained from a 4-dimensional effective Lagrangian that looks like that with the potential energy like that. So let me think a little bit about what we've done over here. If I work with this 4-dimensional Lagrangian, this Lagrangian gives me these equations of motion. If I solve these equations of motion came from an 11-dimensional equation of motion. By solving these two equations of motion, I'm guaranteed to solve the 11-dimensional Einstein equation. If I solve the 11-dimensional Einstein equation, and I've also solved the 11-dimensional 4-form equation, I've solved all the bosonic equations of 11 dimensions. By solving the equations of motion of this 4-dimensional Lagrangian, I have automatically guaranteed to solve the 11-dimensional equations of motion as well. That's the nature of a consistent truncation. I didn't have to appeal to not being able to excite heavy states. I didn't have to appeal to integrating out extra dimensions or anything like that. This is very simple. Solving the 4-dimensional equation of motion guarantees a solution to the 11-dimensional equations of motion. That's the consistent. Let me take just a closer look at the 4-dimensional theory. It's not canonically normalized, but by choosing alpha correctly, I can get a canonically normalized breathing mode scalar. The potential had 2 exponentials, so it's sort of a nonlinear potential. However, if I linearize the potential, I get something like that. This is a constant term. That's the cosmological constant. In fact, this -6 is the correct number, or -6 over L squared. It's the correct number to give me ADS4 with radius L. It has to be. I mean, it has to be consistent. The quadratic term over here is a mass term for the scalar field. It's a real scalar. If it's canonically normalized, the mass term should be 1/2 m squared phi. That means the mass of the scalar is 18 over L squared. Now, I didn't go over the ADS representations, but I at least hinted that the lowest energy eigenvalue E0 is related to the mass of the scalar, or related to the mass of the field. There's an expression that tells you for scalar fields, the mass and E0 relation is written like that. So if I plug in 18 over L squared over here, and I do this computation, I end up with E0 equals 6. E0 equals 6 is the same number. Well, I didn't copy it down before. I didn't copy it down again, but I flipped backwards. I'm going the wrong direction. If I flip backwards enough over here, E0 equals 6 is what I have over here. So in fact, this linearized collision of Klein constants calling this the breathing mode is completely consistent with this phi here being the breathing mode.
The minimum of the potential was a local minimum or the global minimum?
In this case, I believe it is actually I believe it's a global minimum. I don't remember, to be honest. And it'd be very tricky. It's very tricky in some of these cases. This, I think, is a global minimum. And it's two, well, which way does it go? It's two competing exponentials in such a way, I think, that it is a global minimum.
It doesn't look like a bounded from below, the potential.
Oh, wait, this might have been, which way did it go? It might have been global maximum. No, I think it's global minimum.
Goes to infinity under Einstein.
Well, it's a matter of working this out. And I think, global minimum. But you have to be very careful in ADS, because some of these potentials actually turn upside down a little bit. And one side of that is something like a negative mass squared in ADS. But this is the Barton Loader frequency now. You can actually have a little bit of negative m squared in ADS and still be stable. Well, so let me get back to this idea of consistent truncation a little bit. Linearized analysis, you have a whole KK tower in the foreign group in the compactification. DeWitt-Nicolai suggests that if you go to the massless sector, you should end up with n equals 8 supergravity. It should be consistent. If you truncate to the to the singlets on S7, you get a bosonic breathing mode compactification, which is also consistent. But can we do better? If we wanted to have some sort of symmetry principle to guarantee a consistent truncation, we would like to truncate the singlets of something. But it better not be singlets of the full isometry group of SO8. But we can truncate the singlets of some subgroup of SO8. And you have a transitively acting subgroup, which means it doesn't keep any points fixed under the action of your symmetries. And it turns out, by truncating the singlets of a transitively acting subgroup, you actually retain a finite number of states out of the infinite KK. So it's a kind of an interesting thing. And I can find a fairly natural subgroup of SO8 by thinking about the 7th sphere as a Hopf vibration. And this is, I can use a round 7th sphere, but it can be motivated from a squashed 7th sphere compactification, which is to say, 7 dimensions can be split into 1 plus 6. I can write the 7th sphere as a so-called U1 bundle over CP3, or a U1 vibration over CP3. This is not very explicit. What I mean by that is I can write down the CP3 metric over here. This is complex projective 3 complex dimension over here. It's a 6 real dimensional space over here. And I have a 7th dimension over here, which is something like dy squared or so, but it's not a direct product. It's not CP3 times a circle or something like that. This is a circle fiber over here, which depends on the internal coordinates, such that, so I'm writing this in a form notation. I view eta as a 1 form. D eta is 2j. J is the Kähler form on CP3, basically. What happens is the round 7th sphere has an isometry group SO8. CP3 has an isometry group SU4. I have a U1 symmetry from the fiber over here. So in the group theory point of view, the SO8 isometry of the 7th sphere I can decompose under SU4 times U1. there's lots of different ways to embed SO8. There's the so-called triality. But what I have in mind is to take the supercharges, which transform as a spinner of SO8, and they decompose as 6 plus 1 plus 1. So what I'm going to do is I want to truncate the singlets. If I truncate the singlets of SO8, I get rid of the spinner, I get rid of all my supercharges. It's a bosonic truncation. That's the breaking motion. However, if I truncate the singlets of SU4, there's 2 singlets of SU4 over here. So out of 8 gravitinos over here, I end up preserving 2 out of the 8 from a 4-dimensional point of view by getting rid of the 6, getting rid of the non-singlets of SU4. This is a compactification, if I truncate the singlets, to n equals 2 in 4 dimensions. So, if I do that, I can take my SO8 representations, decompose them, look for SU4 singlets, and out of the whole infinite Kaluza-Klein tower, this is the only thing that survives. There's no more n equals 0, 1, 2, 3, 4. The Kaluza-Klein level doesn't go all the way up to infinity. It's a very curious feature. What I find is at Kaluza-Klein level 0, there are 3 states here that survive. There's a graviton, spin 2. There's a gravitino over here, spin 3/2. And there's a graviphoton, spin 1 over here. Graviton, gravitino, graviphoton, that forms an n equals 2 supergravity multiplet in 4 dimensions. Nothing survives from Kaluza-Klein level 1. You jump up to Kaluza-Klein level 2, and these states here survive. And no higher Kaluza-Klein level survives. But the level 2 states are kind of interesting. You have spin 1 over here, several spin 1/2s, and some spin 0s as well. Spin 1, you say, should be like a gauge boson or a vector, but in fact, this has too much energy or too much mass. This is a massive vector. And they have a bunch of scalars over here. The E naught equals 6 scalars. I already identified as the breathing mode. It turns out by writing the 7th sphere as U1 vibration over CP3, I've broken up my 7th sphere metric into 2 parts. It's a fiber part and a CP3 part. I can relatively distort the volume of the fiber versus the CP3. That's called a squashing mode over here. And so I can also have this E naught equals 4 squashing mode turned on. I have some additional scalars here, which we'll identify shortly. If you ask, this is n equals 2 theory in 4 dimensions, I should be able to classify these things. These are sort of on-shell states, or the physical states in the spectrum. And I should be able to try to classify this in terms of n equals 2 supersymmetry. N equals 2 supergravity coupled to matter has a supergravity multiplet, which is corresponding to this stuff over here at Kaluza-Klein level 0. There's also possible vectors and possible hypers. Well, if that's a massive vector, there should be a vector multiplet over here. Just through basic counting, this is not sophisticated. Basic counting, the n equals 2 vector should have a vector and 2 scalars. A massive vector eats up 1 scalar out of a Higgs mechanism. So just from a counting point of view, I should have a massive vector plus 1 scalar. There's 5 scalars over here. So the vector multiplet accounts for 1 out of these 5 scalars. There's 4 more scalars. 4 more scalars organizes into an n equals 2 hyper multiplet. So here, at Kaluza-Klein level 2, that's the content of a massive vector multiplet, which is a 1 hyper coupled to 1 vector. So I gave you a little bit of group theory to say if I truncate the singlets of SD4, this is what you get. It turns out you can actually write down a full nonlinear Kaluza-Klein